Hello everyone. In this video, we're going to look at example 1 in section 14.4. So in this example, we're actually going to be computing a directional derivative by using that formula in the previous theorem. All right, so let's get started. So here we're told to let t be the function of temperature, like we saw in the preliminary example. So this should look very familiar to you. We want to find the directional derivative of t at p, 1, 1, as we move in the direction of q, 1.7, 0.5. So q is the same point that we already saw. The workbook just rounded 1.66 up to 1.7. So we should think of this problem as being the same question that was asked in part B of the preliminary example. But now with this theorem under our belts, we can use a dot product to compute the exact value of this directional derivative. All right, so we want to include units and compare with your answer to part B of the preliminary example. All right, let's go ahead and get started. So the theorem for computing the directional derivative tells us we need to compute the gradient of t and a unit vector in the direction of PQ. So let's do each of those steps. So first of all, the gradient of t at xy, we've actually already computed this in part A of that preliminary example. We saw it was the partial with respect to x at xy times vector I plus t sub y, xy, j. All right, so plugging in those partial derivatives that we already computed, this becomes 1/2 x times I vector. We're going to say minus 1/2 y times j vector. Okay, cool. So we have that first part, that gradient. I'll just highlight it here. Okay, great. So now we need a unit vector in the direction of PQ. So I'm going to write that out. So now we need to find a unit vector in the direction of PQ. I'm just going to draw out points P and Q a little bit. So we saw here P, we're going to label 1, 1. Maybe I'll draw it a little bit better to scale. 1, 1, here's P. We have kind of a set of axes here. And then Q will be somewhere like a little further on the X, a little lower on the Y, down here. Okay, so here's our vector PQ. And in order to make it a unit vector, what we're going to do is divide by the length of PQ. So you might have seen this before in another math class. If you took Math 153 with me, we've seen this in our previous work with vectors, which will look like the following. So our unit vector then is going to be equal to that vector PQ. But now we need to divide by the length of PQ, kind of to normalize it, or to make it have a length of just 1. So first, let's go ahead and compute what that PQ vector is. So to determine the vector PQ, like in components, we have to take the point Q minus the point P. So that's going to look like 1.7, 0.5, minus the point 1, 1. So then in each component, we can look at the x component will be 1.7 minus 1, which will just be 0.8. Oops, 1 too big, not 0.8. Should be 0.7. 0.7 I, that is in the x direction. And then the y direction would just be negative 1/2 or negative 0.5 j. Okay, so there's our vector PQ. Okay, so in our numerator here, we'll have 0.7 I minus 0.5 j And then we're going to divide by the length of PQ. So the length of PQ is the length of this vector here. So that would be the square root of 0.7 squared plus negative 0.5 squared. All right, so if we compute that out, we're going to get a value, a number for that denominator, and we're going to divide each component by that denominator because we have a subtraction in that numerator. So that becomes, and you can check my work, 0.81i minus 0.58j. All right, so there's our unit vector. All right, so let's just recall, what is it we're trying to find? Quick reality check. We want to find the derivative, or the directional derivative, of t at the point 1, 1 in the direction of the vector PQ. Okay, and so to do that, we found the gradient and a unit vector that's in the direction of PQ. So we just need to take the dot product between them. So that'll look like T sub u of 1, 1 is equal to the gradient of T at 1, 1 dotted with our u vector. So that would look like plugging in 1, 1 to our gradient would look like negative 1/2 I minus 1/2 j dotted with 0.81 I minus 0.58 j. So when we do that, we're going to multiply corresponding components and then add the results together. So we should be getting 1/2 times 0.81 minus 1/2 times negative 0.58. I'm running out of room here, which you can check my work is about negative 0.12. And again, our units are going to be degrees Celsius per centimeter. So what we just found is actually how fast the temperature changes at 1, 1 when we move in the direction of Q. And so we can compare our work with that from part B of the preliminary example. In part B, we got negative 0.3. So our estimate was fairly close. We got a negative in both cases, but we're seeing that we get a more precise answer when we look at the directional derivative. All right, great work, everyone.